Hello everyone, welcome to our discussion of section 5.5 where we will be talking about solving exponential equations and logarithmic equations. Before you start this section, make sure you review the logarithmic properties that we discussed in section 5.4. Make sure you remember those. That's essential for knowing how to use which technique in solving these kinds of problems. So, generally speaking, in these two boxes that you see, there are two main techniques that we use to solve these kinds of equations. One is, if you look in this box, in particular this one, is saying that if you have, let's say 2 to x power and equals 2 to 5 power. In other words, if you have the same base, let's say 2, to some different powers, x and 5, then this automatically means that x should be equal to 5, right? So that means if you can rewrite both sides of an equation to the same base, raised to two different powers, then you can equate those powers and solve for the x. That's one technique we're going to be using. Another technique is that you can take the log or natural log of both sides in order to solve the equation for any variables that you might have. So these are two different techniques. And make sure, please, you read all of this. This is all for your reading before you start attempting the first example. Like I've asked you to do in all the previous videos, first, pause the video, make sure you solve this problem on your own, and then compare your solution with the ones that I have in the video. So come back to the video in order to compare your solutions with this. So I'm assuming you've done that. For example, in this case, you already have the solution for x. You already know what x is. So the technique we have here is that 32, we can rewrite 32 in some power of 2, right? So let's do that. So we can say 2 to the x equals 2 to the 5 power. This automatically means, if this equation is to be true, that automatically means that x should be equal to 5. Okay, so that's one technique we can use right away there. I hope this agrees with what you have. Now this one. So I'm assuming that you've already solved this for x and you're going to compare your solution with this. So the first thing I do is I look at the numbers on both sides and I notice that, okay, I can rewrite, because on the left I have 4 written to some power, right? Can I write 16 to some power? The answer is yes. So let me do that. So I keep the left side the same, and I write the right side as 4 squared, right? So if this equation is to be true, then we must have the powers equal to each other, right? Because the bases are equal to each other. The bases are 4. So therefore, 3x minus 5 must also be equal to 2. So let's solve this equation for x. So we have 3x equals 5 plus 2, or 3x equals 7. Therefore, x equals 7 over 3. Right? So that's the solution for that. Part C, same idea. You take a look at both sides and see if you can write the right side to some power of base 3. Some power of base 3, because on this side the base of that exponential function is 3. And the answer is yes. So let's see, and again I'm assuming you've already answered this on your own, and you're going to compare your solution with this. So first thing, I will write 27 as 3 cubed, right? Then I know that I can rewrite this using powers or properties of exponents as equal to 3 to minus 3 power. Right? Now, usually, as you know, we don't like to write the powers in negative form, but in this case, it's actually useful. It's useful because now I have both sides of this equation written to the same base, raised to different powers. So if this equation is to hold, then the powers should be equal to each other because the bases are already equal to each other. So we say x squared, so therefore, x squared plus 4x should be equal to minus 3. Okay, so this gives us a quadratic equation, right? If I move the negative 3 from right to left, what do I get? I get x squared plus 4x plus 3 equals to 0. Then if we can factor this quadratic equation right away, we will do that because it's the easier and quickest way of solving a quadratic equation like this. But if I can't factor this, then I can surely use the quadratic formula. But in this case, fortunately, this is an easily factorable equation. We can say that this equation has factors x plus 3 times x plus 1, right? So therefore, let us set each factor equal to 0 and solve for x. If x plus 3 equals 0, then x equals minus 3. That's one solution. And if x plus 1 equals 0, then x equals minus 1. That's the other solution. Okay, so this is basically how we go about solving this. I hope this is what you got also. So moving ahead to the next one. Now, when you take a look at this one, we can't really write both sides of this equation to the same base, right? There's no way we can write 28 to some base that is equal to the same base of 10. So in situation like this, then we will use the other technique, which is take the log or natural log of both sides. Now, if this base was e, or that one was e, I would take the natural log of both sides because it's easier. You can either way, you can take either the log of both sides or the natural log of both sides, but depending on these numbers, sometimes it's easier to use either natural log or log. If it was e, if this base was e, I would use natural log. But because it's 10, it's easier to actually use log. Now, before I do that, why am I doing that? Now, if you recall, in worksheet 5.4, the one previous to this, we said that if you have the log of an expression, you can bring the power down and in front. You can do that, and that's useful because then you can solve for x. Right? Right now, we can't solve for x as it is. So we need to bring the x down. So let's take the log of both sides. So log of 28 to x power equals log of 10 to minus 3x power. That will allow me to bring this x down and in front, and I can do the same thing with this power. I can bring it down and in front. So I have x times log of 28. I'm just using the parentheses for clarity. It has some uses. You'll see that in a minute, but you can use it for clarity and or for correctness. So use parentheses. They're quite useful. The next one, we have negative 3x coming down and in front times log of 10, right? So now, from the properties of logs, we know that log of 10 is equal to 1, right? In fact, what we learned in section 5.4 is that log of anything to the same base is always equal to 1. So log of, let's say, 8 to base 8 is also equal to 1. Okay, so we know that. Then this will give us x times log of 28 equals minus 3x. Is there a class here? Is there a class here?
Sorry, no, I just came from this classroom and I took an exam and I was going to see if I left my glasses.
Go ahead.
Okay.
Yeah, you bet.
So sorry.
Yeah, no problem. So in this case, we have this equation, but we can't really cancel out the x terms. If there were numbers, we could cancel them, but we can't cancel x terms. So we have to bring both x terms to one side and factor the x. So let's do that. X times log of 28 plus 3x equals 0. And then we can now factor the x. Remember, you cannot factor x from this, you cannot cancel the x from the expression. Okay, you have to factor it out. So x times log of 28 plus 3 equals 0. Now, this piece, it's not going to be 0, right? You can actually calculate that. Use your calculator. Calculate log of 28 plus 3. It's some non-zero value times x, right? So the only way this equation can be true is if x is equal to 0. Okay. All right, so that's the solution of that, and you can test it. That's the only value for which, if you plug it into the power there, you can get 1. You get 1. Anything to 0 power is 1, and both sides of the equation will be true. Okay, so I hope that made sense. And so here we have, and sorry, by the way, earlier some people were here to look for their stuff that they thought they left behind. That's why I had to ask them if they had a class here. That's what you heard earlier. So this particular one, if you haven't solved this yet, go ahead, solve this. And so pause the video, do that, and when you come back, you can compare your solution with this. So I'm assuming you've done that. Now we have to solve for t, but notice in this case, the base on the left side is e. Okay, so in order to solve for t, you know I have to bring this t down and in front. So how do I do that? I can take either the log or natural log of both sides, right? Or natural log. Which one do I do? I choose natural log because it makes calculations a little bit easier. So let's do that. So we will take the natural log of e to 4t power equals natural log of 200. And so on the left, this power comes down and in front. So we end up with 4t, I'll just put it in parentheses for the sake of clarity, times natural log of e, and then I have natural log of 200. For now, I keep it like that. But we know that from section 5.4, we know that natural log of e is equal to 1. Okay, so then that gives us 4t equals natural log of 200, right? So we can solve for t, saying that, okay, t is equal to natural log of 200 divided by 4. So you can leave your answer like this. This is just fine. So this is exact form. This answer is in exact form. Or if the question says on the assignments or on an exam, if it says round your answer to, let's say, 4 decimal values, you can calculate that and write this is equal to 1.3246. So depending on what is the question asking. Is it asking you to leave your answer in exact form? That's what they mean, in fraction form. Do they mean, are they asking you to write your answer in decimal form, or some in this kind of a form? So you can do that. All right. So here's the next one, part F. Same scenario, right? So I'm assuming that you've already solved this. If you haven't, just pause the video and do it, and then come back to the video. But you can see the base here is again e, right? So it's easier if we take the natural log of both sides, right? Natural log of 0.04 on the right. And then this allows us to bring this power down and in front. So we say minus t times natural log of e equals natural log of 0.04. Now, we know natural log of e is equal to 1. So that gives us minus t on the left equal to natural log of 0.04, right? And so you can, in order to solve for t, you can multiply both sides by -1. So then you can do multiply both sides by -1, and what do we get? We get t on the left, we get minus natural log of 0.04 on the right. So that's a solution. Or if you're asked to, so this is exact form. So this is exact form of a solution. And giving the same answer in decimal form, you can calculate this using your calculator. You'll notice that if you calculate natural log of 0.04, you get a negative number. Then that negative number gets multiplied by this negative number in front, and it will give us a positive result. So 3.2189. So this answer is in decimal form. Okay, I hope this is making sense. Okay, so we can move forward. And of course, you can come by my office hours if you have any questions about any of this. So this one is an interesting one. Go ahead, solve this. See what answer you will get for t, for variable t. When you're done, come back to this. Now, I'm assuming you've done that. So there are two ways of going about solving for t here. One is that you can right away take the log of both sides as it is. Just like this, you can take the log. This is not incorrect, but it makes this problem unnecessarily complicated. So the easier path would be to first get rid of this 1,000. Because your objective is to get to this t, right? You want to solve for this t, which means you need to isolate the t eventually. So take steps in isolating t in a way that maybe it's easier path. One way is to first get rid of this. And how do we do that? We can divide both sides by 1,000 to get rid of that 1,000 in front, right? So then the 1,000 can cancel out. We can get e to 0.09t equals 5 on the right side, right? Now, because this base is e and there is no number in front, you see that? That number in front is gone. So this is considerably simpler to take the natural log of. Let's go ahead and take the natural log of both sides. So natural log of e to 0.09t equals natural log of 5. Okay, what does this do? This will allow me to bring this power down and in front. Okay, so if I do that, I will get 0.09t, right, times natural log of e equals natural log of 5, right? You already know that natural log of e is equal to 1. So on the left, we have 0.09t equals natural log of 5. And then from here, we can say that t is equal to natural log of 5 divided by 0.09, right? So this answer again is in exact form, all right? Exact form. A lot of times, it's useful to leave the answer in exact form, just like that. But if the question asks you to find the answer to, let's say, 3 decimal values, you can use your calculator to find natural log of 5, divide that by 0.09, and you will get t is equal to 17.883. Okay, so that's decimal form. Okay, I hope this is making sense. So here we have another equation to solve. It's an exponential equation for us to solve. Well, as long as pause the video and then come back to it after you have your own solution written down. Okay? Because I want you to learn this quickly and effectively. And the way to do it is like that. Do not skip your own solution. Your solution is more important than this. Okay, so you know that this power has to be brought down on both sides in order for us to solve for x, right? Okay, so how do we accomplish that? We have a very useful tool. It's called the log. So let's take the log of both sides. Log of 5 to x plus 2 power equals log of 4 to 1 minus x power. Now, notice in this power you have 2 terms, right? X plus 2, you have 2 terms in this one. So when you bring this down, when you bring this power down and in front, make sure you put it inside a parenthesis. It's very, very important. In this case, putting that x plus 2 and 1 minus x in a parenthesis is not optional. You have to do it. If you don't put the terms inside a parenthesis, then your answer will end up not working out correctly. Okay, so put x plus 2 in a parenthesis, multiply it by log of 5. The parenthesis here ensures that you will distribute log of 5 to both 2 and x, whereas if you don't use the parentheses, you will only multiply log of 5 by 2, but not by x. Okay, so that's on the left side. On the right side, once again, we put 1 minus x inside the parentheses times log of 4. Now we can distribute, right? We have to distribute in order to get the x term by itself. So let's do that. So we have x times log of 5 plus 2 times log of 5 equals log of 4 minus x times log of 4. All right. So notice you're solving for variable x. Where does x occur? It occurs here and here, right? In 2 terms. Because of that, we have to move both terms to one side and isolate them. So let's do that. We're going to keep this term on the left. We're going to move this one from right to left. And when we do that, it'll change from negative to positive, x times log of 4. Then on the right side, we keep log of 4 where it is. Then we move this 2 log of 5 from left to right, right? Because we're isolating the x terms from the constant terms. Don't forget to change this algebraic sign from positive to negative when you move plus or positive 2 log 5 from left to right. So it's going to be minus 2 times log of 5. Okay. Now we're a little bit closer to solving for x. So what do we do now? We're solving for x, and x is occurring in 2 terms. Well, solving means isolating the variable. So in order to solve this variable, we need to factor it out. So let's do that. We say factor x out on the inside the parentheses, we have log 5 plus log 4. Remember that factoring is the opposite of the distributive property. So if you have doubts about whether your factorization is correct or not, just redistribute x into this parentheses and ask yourself, do you get that, the expression that you started with? If you do, that means your factorization is correct. You don't need to doubt the factorization. So the right side will be log of 4 minus 2 log 5. Now we can solve for x, right? We can say x is all of this divided by whatever we have in this parentheses, right? So it's log of 4 minus 2 log 5 divided by log 5 plus log 4. So this is one form of valid answer for this problem, but it's in exact form, right? If you're asked to write this in decimal form, then you'll have to calculate all these logs. Because I'm running out of space here, let me put that here. I've done that. And I got, for the numerator, I calculated log of 4 and 2 log of 5, and then I subtracted them from each other, and I got minus 0.79588 divided by 1.3010. And then, of course, after you divide that, you get minus 0.6117. So these two answers are different forms of the same thing, of the same x value. One is in exact form, the other one is in decimal form like that. All right. So let us go to the next one. And I'm just double checking my values. Okay, they seem to be okay. So this next one, and hopefully it's clear on the screen, that one. So go ahead, solve that, and when you're done, you can come back and compare your solutions with what I have here. I'm assuming you've done that. Okay, so we have, again, we have to bring the x terms down in order to solve for it, right? So let's take the log of both sides. Like that. This allows us to bring the powers down and in front. Notice that on the left you have two terms in the power, right? So make sure you put them inside parentheses. So you say x plus 1 times log of 2 equals 2x times log of 5. So now on the left, distribute the log of 2 into the parentheses. So we have x times log of 2 plus log of 2 equals 2x log of 5, right? Okay, so we have, notice that the x terms are scattered here and here. So we need to pull these to one side. So x log of 2 minus 2x log of 5 equals minus log of 2. You see what I did? I just moved this log of 2 from left to right. So now let's factor the x out, because solving is about isolating. So factor the x out. So we have x times log of 2 minus 2 times log of 5 equals minus log of 2. And of course, then the next step is just to solve for x by dividing this by everything in this parentheses, right? So we have minus log of 2 divided by log of 2 minus 2 log of 5. You can put this minus that you see here, you can put that in front of the fraction. Okay, you can do that too if you want to. So in that case, then we have, let's see, so I guess I have enough room here. I can do that here at the bottom. So, or, let me just say, or, if you put this, you can bring this minus, multiply it by both terms in the denominator and get rid of it that way. You can simplify it. So what I've shown in the box is already okay. But if you want, you can also show the answer like this. Log of 2 divided by 2 log of 5 minus log of 2. Okay, so that's another form of giving the answer. Use whichever one you're comfortable with. It doesn't really make any difference. And of course, if the question is asking you to calculate the number itself, then you can do that. You can calculate the numerator, which is 0.30103, divided by let's see, 1.39794 minus 0.30103, and that gives you x equals 0.2744, like that. Okay. All right. So this is, I hope this is helpful. Now this next problem is an interesting one. So try it. Try it on your own. See what answer you will get, and then come back and compare it with this. And I'm assuming you've done that. So we can go about solving this. All right. So looking at this, the first thing that I look at that catches my attention is this term, because it has a negative x power, right? So I tend to want to rewrite that with positive power. So I write e to the x minus 6 times 1 over e to the x equals 1. So I took this e to the minus 6 and rewrote it like 1 over e to the x with positive power. What does this give me? Well, it gives me an equation with no negative power, right? So let me change it a little bit, or simplify it a little bit like this. So I move the 1 from right to left, so that's what I get. Now what do I do? Well, we typically don't like fractions, right? None of us like the fractions. So let's take the common denominator. Maybe we can get rid of that fraction. So the common denominator is e to the x. The denominator here is 1. The denominator here is also 1. So compare this denominator with that. What's missing from it? Everything, e to the x, right? So multiply the top by what's missing from the common denominator. You get e to the x times e to the x. Minus, you have minus 6, and then compare this denominator with that. What's missing? Nothing. So you don't multiply minus 6 by anything. You just keep it like that. Compare the common denominator with this. What's missing? Everything. E to the x is missing, so you multiply minus 1 by e to the x, you get minus e to the x, and the right side is going to be equal to 0. Now, at this point, you look at this equation, and the right side is equal to 0. But if that's the case, the only way this equation can be true is if the numerator is 0. Because the denominator is never 0. The denominator will never, ever be 0. So the only way for this equation to hold is if the numerator is 0. So let's first of all clean it up a little bit. E to the x times e to the x is equal to e to 2x. And then minus e to the x, I'm just putting the terms in order, minus 6 over e to the x equals 0, isn't it? So then we know for this equation to hold, the only way that could be true is if the numerator is equal to 0. So let's set it equal to 0 and solve for x. Fortunately, in this case, this expression is easily factorable. You can say that e to the x here, e to the x here, then we're looking for two numbers such that they multiply to that and they add to minus 1. So what two numbers do you know that multiply to negative 6 and they add up to give you negative 1? Negative 3 and 2, right? If you said negative 3 and 2, you're 100% correct. So let's, so I'm going to put negative 3 here and plus 2 here. And surely that's the correct factorization. Okay? Now that we have the correct factorization, let's solve for x from each factor. I'm going to move this a little bit so it's at the center of the page. Now we say, okay, from this factor, and then we'll do the same thing for that one, we have e to the x minus 3 equals 0, then e to the x can be equal to 3, right? And then how do we solve for x? Take the natural log of both sides. So we get natural log of e to the x equals natural log of 3. Then x can come down and in front. So we get x times natural log of e is equal to natural log of 3. And you know that natural log of e is equal to 1. So you get from here x equals natural log of 3. That's one solution for x. What about the other side? Well, let's find out. So we have, and I can actually put it a little bit here. So we have e to the x plus 2 equals to 0. Then solve for x, which means isolate x. So now let's take the natural log of both sides, right? We say natural log of e to the x equals natural log of negative 2. And oops, you have to stop, right? Do you see why you have to stop right away? Because log or natural log of a negative number is undefined. So what happens now? Well, we say no solution. Because of this, we have no solution for this factor. From this factor, we have no solution, and we just showed that. So we say that, and no solution on that side. So the only valid solution here is just this natural log of 3. Okay. All right. So solving logarithmic equations. So this is basically the same thing we did, but take a look at these equations. These are a little more interesting, a little more challenging, and also they require us to use those properties of logarithmic expressions that we haven't used yet. Remember what we talked about in section 5.4? There's a whole bunch of those properties of logs, right? We haven't used many of them. So from this point forward, we have to do that. So let's do that. Okay. And also, please make sure you read all of this, right? This is for your reading, everything that you see here. All right. So this one says solve the following logarithmic equation. And there's a bunch of them here for us to solve. So how would you solve this? Don't look at, I'm going to start solving this, but don't look at that. Just pause the video, solve it on your own. How could you solve this? We've talked about one particular technique in section 5.4. Okay, I'm assuming you've done that and now you're back. Remember that when it's useful, not all the time, when it's useful, you can write logarithmic expression into exponential forms, or you can write exponential forms in logarithmic forms when it suits your purpose. In this case, it does, right? So you can see the base is 2. We know that log expressions generate an exponent. So we already know -3 is an exponent to base 2, right? So we can say 2 to that exponent is equal to x. And we're almost done, right? 2 to -3 power, it's going to be 1 over 2 cubed, and that's going to be x equals 1 over 8, right? We can quickly solve that. So there it is. All right, so just by converting the log into an exponential form, we were able to solve it very, very easily. All right, so next one. How would you solve this? I'm counting on you. I'm counting on you that you're pausing the video. You're not looking at my solutions right away. I'm counting on that, okay? That's key to your success in understanding all quantitative subjects, like physics, this one, chemistry, economics, anything. First, come up with your solution, then compare it with somebody else's solution. All right, so in this case, because we have a natural log, then the base has to be e, right? So we know log or natural logs produce an exponent. So -2 is an exponent. So let's write this in exponential form once more. So e to -2 power is equal to x. So we can actually leave the answer like that. We've already solved for x. Or if you're asked to give the answer in some kind of a decimal form, then you can use your calculator to calculate this, and you'll get 0.13534. Okay, either or, depending on what the question is asking. Okay, so this one, how would you solve that? I'm assuming that you have your solution in front of you. That would be great. So notice that log or natural log expressions generate an exponent. So that x is an exponent. To what base? To whatever the base is for the log expression. So we can rewrite this as 125 to x power is equal to 1 over 25, right? Well, the 125 and 25, we're kind of familiar with their factors, right? Because if 125, you can write it as 125, we can say it's equal to 5 cubed, right? And 25, we can say that's equal to 5 squared. The nice thing here then is that you can write 125 to some power of base 5, and you can write 25 to some power of base 5 again. So that's nice. So let's do that. So we're going to replace in here, we're going to replace 125 with 5 cubed inside the parentheses with x on the outside, right? So I kept the x right there on the outside, equals 1 over 5 squared, isn't it? Now, I'm going to use the properties of exponents and say that the inside and outside powers always multiply each other. So instead of 5 cubed to x power, I can write 5 to 3x power, right? That's the properties of exponents that we learned about maybe in pre-algebra, right? So here we're just applying it. And then I can rewrite the right side with as 5 to negative 2 power. I can simply bring the 5 squared up, and that will make the power negative, which is, of course, another property of exponents. So now take a look at these. Now, the bases are the same, 5, right? So if I'm solving for x in an equation like this, so the powers should also be equal to each other. So let's set the powers equal to each other. We have 3x. So we can say therefore or thus 3x should be equal to minus 2, and therefore x should be equal to minus 2/3, like that. Okay, so then you can either give the answer like that, or you can say x is equal to minus 0.66667, right? Just giving it in decimal form. So again, this is in exact form, and this is just in decimal form. Like that. All right. So what would you do in the next one? Right? How would you solve this? Have you tried it? Do you have your solution in front of you? Fantastic. So then that technique we've been using so far is still useful. We can rewrite this logarithmic expression in exponential form and then solve for x. So we know log expressions generate an exponent, right? So that 3 must be an exponent. But to what base? To base 5. So we say 5 cubed equals that result, 8 minus 7x. So on the left, we have, of course, 125 equals 8 minus 7x. Then we can solve for x by isolating the x term, like that. And then 7x equals minus 117. And of course, x equals minus 117 over 7. Okay, we can leave the answer in exact form like that. Okay, so let's move forward. Here's an interesting one. We haven't used this property before on this worksheet, so it would be good to use that. Remember this? Which property is this? So let me explain how. I hope you already have your answer, by the way, already. But when I look at this, and it's clear that they want us to solve for x, right? But x is happening in 2 log expressions, not 1, in 2. So it won't help us if we do what we did before, which is convert the expression into an exponential form. If you have just 1 log, that would work. Log expression, it would work. But if you have 2, it's not going to work. So first thing we need to do is we need to combine these 2 terms that my arrows are pointing to. Now in section 5.4, we learned that if you have a log of some expression plus log of another expression to the same base 2, then you can convert this addition problem to a multiplication problem. In other words, we can write log to base 2 of x plus 1 times x minus 1, let me put that in bracket, equals 3. This is one of the properties we saw in section 5.4, and it's also on your formula sheet. So all you have to do is know how to use it. Okay, so now take a look at what we have on the inside. These 2 guys are, what are they? Do you recognize it? They are conjugates. If you remember that if you can see visually that they're conjugates, that's excellent. So you have 2 terms, 2 identical terms being multiplied by each other. The only difference is the algebraic sign in the middle. These are conjugates. So if they're conjugates, then we can apply that shortcut formula that says if you have two conjugates multiplied by each other, then the result you can easily have it as x squared minus 1 in this case. Right? So let's condense this expression a little more and write log to base 2 of x squared minus 1 equals 3. Right? So now we went from 2 log expressions to just 1. You see that? A very important transition, because now you can do what you did before and rewrite this in exponential form. So you know log expressions produce an exponent, right? Okay, great. So we know that's the 3 is an exponent. To what base? To the base of the log. So we say 2 cubed equals that result x squared minus 1. You see how nicely this works out? Then what? Well, on the left we have 8. 2 cubed is 8. On the right we have x squared minus 1. So let's move the negative 1 from right to left. We get 8 plus 1 equals x squared. And then we get x squared equals, let me correct that. We get x squared equals 9, right? What do we do now? I'm sure you remember. We take the square root of both sides, right? So take the square root of both sides. What this will do, the right side, it will be plus or minus using the square root property. Remember that? If you don't remember square root property, just look it up. It's called square root property. The other side gets plus or minus. And so we end up with x equaling plus or minus 3. But if you know, so this is so far it tells us that this should be our solution. But with these problems, we can't just accept these solutions right away. We need to look back and see if they check out. So let's check back with this expression. We're going to check back with this expression, right? So plug in with positive 3. Positive 3, positive 3. Nothing is, everything is good. So 3 log of 4 to base 2 is okay. Log of 2 to base 2 is also okay, right? But if you plug in negative 3, if you substitute negative 3 here and here, what do you get? You get log to base 2 of negative 2 plus log to base 2 of negative 4 equals 3, right? That's what you get if you substitute for x with negative 3. But we know that log of negative numbers is undefined. That's undefined. So therefore, we can only accept one of those solutions, not both. We can only accept log of 3, but not log of negative, we can only accept x equals 3, but not the x equals negative 3. So let me do it this way. Let me write it separately first. So x equals 3, x equals negative 3. Now that one we just checked. It's not a solution. So the only valid solution is this one. So the only valid solution. Okay, so you have to check back, make sure that the x values that you obtain check out in the original expression. Okay, so we move forward. Here's another one. So go ahead, if you haven't used this property from section 5.4, go ahead, use that property, and then when you're done, come back here and compare your solution. So I'm assuming that you've done that. So then the first thing you should notice is that you have x terms in all of these three terms, right? So the term that you're solving for is in three different log expressions, and the definition of solving is that you have to isolate that. So you have to combine these log expressions somehow. Well, how do we do that? In section 5. And by the way, notice that they're all to base 3, right? They're all to base 3. Therefore, those properties that we learned about in section 5.4 can be applied. So using those properties, we can write a subtraction expression like this we can convert it into a division problem. So log to base 3 of x plus 14 divided by x plus 6 is equal to log of x to base 3, right? Using those properties. If you don't remember it, please look it up. It's very important that you know how to use those properties. So what do we do now? How can you proceed from this point forward? Notice that the left side and the right side can only be equal if this piece is equal to this piece, isn't it? There's no other way that this equation can be true, because the bases are both sides are logs, and the base is also 3 for both log expressions. So if this equation is to hold, we should be able to say, okay, therefore x plus 14 over x plus 6 must be equal to x. Okay, so all right, so let's in this case we can cross multiply. So we know that the denominator of x here is 1. So cross multiply, by that I mean multiply that and multiply these two together to get it out of this fraction form. So you can do x plus 14 times 1 equals x times x plus 6, right? So then let's simplify this a little more. What do we get? We get x plus 14 equals x squared plus 6x. You can see what this is shaping up to be, right? It's shaping up to be a quadratic equation. So let's move these two terms with those and set the other side equal to 0. So x squared plus 6x minus x minus 14 equals to 0. Let's combine these two x terms. What do we get? I'm running out of room here. Let me move up here. So we will get x squared plus 5x minus 14, right, equals to 0. Now we ask, what two values multiply to give us negative 14 and add up to give us 5? What two numbers do that? They multiply to negative 14 to give us negative 14. They add up to give us 5. So the only two numbers I can think of are 7 and negative 2, right? You multiply 7 by negative 2, you get negative 14. You add 7 and negative 2, you get positive 5. Okay, so now that's nice, because that means we don't have to use the quadratic formula. We can just say x plus 7 times x minus 2 equals to 0, right? It's a lot less time consuming if we can factor an expression. So now let's set x plus 7 equals to 0. That means x equals to negative 7. On the other side, if you set x minus 2 equals 0, that means x can be equal to 2. Now, we can't accept these right away, these solutions right away. So we need to check x minus 7 and x plus 2 in the original expression. So here, if you plug in negative 7, it's okay. You end up with a positive value, right? Negative 7 plus 14 gives you positive 7. But hold on a second, if you put negative 7 here, oops, we get a negative 7 plus 6, we get negative 1. That's bad. And if we put negative 7 here, that's bad, because it's undefined. The log of a negative number is undefined. So we can't do that. So negative 7 is out of the question. In other words, we're saying that negative 7 is not in the domain of that functions, those functions that we have. So that's not acceptable. But if you put 2, if we put x equals 2, you'll see that you get positive values in all these log expressions, right? If you put 2 there, you get log of 16 in here, you get log of 8 here, you get log of 2 to base 3 there. So it'll work out. Okay? So, like that. All right. Sometimes, even with x equals 2, even though if in terms of number 2 being in the domain of each of these functions, sometimes when you check, you'll notice that this side you get a different value than this side. You get a different value on both sides. In such cases, you would have to also exclude x equals 2 if that happens. So watch out for those situations too, that when you plug in a value, you get different values on either side of the equation. In such cases, you have to exclude both numbers. So you would end up saying no solution. But in this case, the 2 will work out. Okay? Okay, so let's move forward with this. So how would you go about solving this? The first thing that should catch your attention, and I hope you've already solved this on your own, is that the x that you're solving for is occurring in 2 terms, not 1. So that means you need to combine those 2 terms. How do we combine them? We can do that using the properties we saw in section 5.4. That's a subtraction operation on the left. We can change that to a division operation, like that. Right? Like that. Now what do we do? Well, on the left you have a natural log. On the right you have a natural log. So if this equation is to hold, then all this expression should be equal to 4. So that we can do that then. We can say therefore x plus 1 over x should be equal to 4. And then you can do the basic algebra for this. You know the denominator here is 1. You can cross multiply, right? You get x plus 1 times 1 equals x times 4. And what do we get? We get x plus 1 equals 4x. Move this x to the other side. You get 1 equals 4x minus x. 1 equal, let me correct that. So 4x minus x. So we get 1 equals 3x. And x equals 1 over 3. Okay, so this will be our solution there. It's not a negative number, so we don't have to worry about it not being in the domain of the natural log function. And finally, this last one. So notice that x that we're looking for is occurring in 3 different terms. Okay, great. So then we have to combine what's on the left. We have to make it into 1 term. It's a plus, so we can convert this to a multiplication operation. So natural log of x plus 8 times x minus 1 equals 2 times, and there's a property that says if you have a number in front of a log or natural log, you can convert it to a power. So we can write natural log of x squared. Okay, that's one of the properties that we have in section 5.4. It's listed there, so please look it up if you don't remember it. So what do we do now? Well, if this is true, if this equation is to hold, then whatever we have inside the bracket should be equal to x squared, right? So because both sides are natural logs, that's why we can say that. Therefore, we can write x plus 8 times x minus 1 should be equal to x squared. Now, if we distribute the left side, we have x squared minus x plus 8x minus 8 equals x squared. And I'm double checking this to make sure, yeah. And then combine these x terms together. What do we get? We get x squared plus, let's see, we get x squared plus 7x minus 8 equals x squared. But something interesting happens, because if you move this x squared from right to left, it'll get canceled with this one. So let's do that. That's actually to our advantage. So we have x squared, which is this one. Then I'm going to move this from right to left. It's going to be minus x squared. And then I have plus 7x minus 8. The other side is going to be equal to 0, right? Once I move the x squared from that side to that, the right side will be 0. So now we have these two that add up to 0. 7x minus 8 equals to 0. And then solving for x, we have 7x equals 8. And finally, x equals 8 over 7. So it's a positive number, and it does not violate the law that log or natural log of a negative number is undefined. So we don't have to worry about that. It's a positive value. Okay? But do double check these anyway, just to make sure that the left side, when you check, is equal to the right side. Okay? All right, so this is the end of this worksheet. If you had your own solutions in front of you as you went through all this, I'm sure you benefited from this a great deal. But if you just watched me go through all of this, I don't think it benefited you as much, but it's not too late. If you didn't have your solutions in front of you, you can repeat this. Just download the blank worksheet, solve every problem on your own, and then come back to these solutions. And I'm sure you'll benefit from all of this as much. Well, okay. So for now, take care, and I'll see you in class.